Hi everyone, my name is Muchana and I'm a graduate student at the University of Florida doing my master's in ECE, and this is my course project for EEL6825 Pattern Recognition Spring 2019, and the topic is access control with real-time face detection and recognition using LBPH face recognizer. So first let's talk about the relevance of face detection and recognition in biometrics. So, biometrics authentication is immensely popular these days because it's a very good way of authenticating someone, providing access control, detecting fraud, and identifying criminals. And this is possible because it utilizes what makes a person unique or individual, like their DNA, their fingerprint, their iris, or their face. And face detection and recognition in biometrics has become immensely relevant these days because of how easy it is to use and implement. All you really need is just a really high quality camera and a very good algorithm. And both of these things can be easily installed in simple devices like your laptop or your smartphone. And I'm sure a lot of you have smartphones that implement face recognition as a method of access control. So today we're going to be implementing that. So first, we're going to talk about some common face recognition algorithms that are being used. So we have eigenfaces, which uses principal component analysis. So it tries to use PCA for dimensionality reduction by looking at the training data or the training images in a holistic manner. Then we have Fisher faces, which is an improvement over eigenfaces. It uses linear discriminant analysis in its dimensionality reduction, and it again looks at the entire training image as a whole. Lastly, we have Local Binary Patterns Histograms, or LBPH, which is what we will be using in our algorithm. This is very different from the first two eigenfaces and Fisher faces approaches because it doesn't look at the training images as a whole, but instead it chooses to look at individual parts of each and every image. So it looks at every single pixel throughout the image and it focuses on a central pixel in one part. It then compares itself to the neighboring pixels and it considers the result as a binary number and then as a histogram. So we'll talk more about this later. But first, we will talk about another classifier that we are going to use, and this is the Haar Cascade classifier. So Haar Cascades is essentially a machine learning based approach where a cascade function is trained from a lot of positive and negative images. It is used to detect objects in other images. So this essentially has a few features like the Haar feature selection, creating integral images, and cascading classifiers. Now, the first step is to collect the Haar features. As you can see on the left-hand side image, we have the edge features, line features, and center surround features. A Haar feature considers adjacent rectangular regions at a specified location in a direction window. It sums up the pixel intensities in each region and then it calculates the difference between these sums. Integral images are used to make this process a lot faster. So amongst the features that are collected, most of them are irrelevant. So its job is to try to identify which ones are relevant from the irrelevant ones. And it does this by superimposing the positive image over a set of negative ones. On the right hand side, we can see how Haar features are used to detect a theoretical face. So you would have the eyes, the nose, and the mouth. So essentially, this stage of the algorithm is going to be used in face detection and feature extraction, in which you are trying to identify how a face looks different from, say, your hand. And you are just going to know that what a face is. It has two eyes, it has one nose, it has one mouth, it has hair, so things like that. Then we move on to the local binary patterns histogram face recognizer. This is used in the face recognition part of the problem. So once we have identified a face and we know what a face looks like, we're trying to pinpoint whom this face belongs to. Now, LBPH works by looking at every single point of the image, as we said before. So let's see how that happens. If you look on the left-hand side of the image, you're going to see that there are some pixels that are being generated from each local point. And you're going to have a central pixel. You're going to compare the central pixel with its neighboring pixels. If the neighboring pixels values are lower than the central pixel, it's going to be written as 0. And if the values are greater or equal to the central pixel, it's going to be rewritten as 1. Thus, you can make a binary pattern out of each individual pixel matrix that you have. Hence the name local binary patterns. And from these binary patterns, you can convert them into decimal patterns. These decimal patterns are plotted on histograms. Hence, each single image is going to generate a lot of decimal numbers, and these numbers are going to be plotted on histograms. For our algorithm, we're going to be using 100 training images, so we're going to have 100 training histograms. It's a significant improvement over eigenfaces and Fisher faces, as both of these get really affected by the kind of light and environment that you're in, because they try to look at the image as a whole. However, since LBPH tries to look at every single point of the image, it's more likely to identify your face in different lighting conditions. We'll get more into the details of how LBPH works soon. So let's talk about the methodology that's being used here. We have three essential modules to the program. So firstly, we have the pre-processing and the face detection, in which we pre-process the images and we make a training database. We have 100 training images for this. Next, we have the feature extraction, in which we have the Haar features of the Cascade classifier, we have the integral images and the Cascade classifier itself working together to extract the features of an image to try to identify a person. And then it goes on to train the model. So the model training is done with the LBPH face recognizer, as mentioned before. And finally, we have the face recognition module, in which we test it in real time using the LBPH face recognizer. So the tools used for this project are Python 3.7.1 in Anaconda Spyder console, and we use the library OpenCV to get our Cascade classifier and our LBPH classifier. So as we mentioned before, for training, we take 100 sample images of the user for whom the access control is being provided. For this, we are taking the Haar Cascades frontal face profile, and we are generating 100 histograms for this. The algorithm crops the images into 200 and cross 200 pixel values. It reduces the RGB images into grayscale so that it's easier for the algorithm to process the histograms. Now, during testing, the algorithm does the same thing again for each test image. So it's going to have a bunch of training histograms and test histograms. It's going to try to compare the two histograms, and it's going to try to get a match. So if a test histogram matches the training histograms, then definitely the algorithm is going to deduce that this is the user, and it's going to give you a confidence score or an accuracy score of how much it matches the user based on that. So here are some of the test results that we have, and we'll go into the demo in a bit. As you can see on the upper left image, that's me. So the algorithm is able to identify me very accurately with an accuracy of 91.42%. The highest I've achieved yet is around 94%, and it unlocks the device when I'm the user. If you look at the bottom left and the top right images, you're going to see that these are two different users which the algorithm does not recognize. So it says that it's not quite similar to what the user looks like, and it keeps the device locked. And if you look at the bottom right image, if you tilt your head too much, it's not going to be able to detect a face, and that's because we're using the Haar Cascades frontal face classifier, as we've mentioned before. However, if you tilt it slightly, say 15 degrees left or right, it's still going to be able to identify. So, and here is the evaluation part. As I told you before, that the highest I have achieved with this is around 94%. The average is around 89%, and in the left hand side of the image you're going to see a confidence plot generated by the algorithm. When the user just looks into the webcam for a certain amount of time, you can see that the average score in there is pretty high. Now on the right hand side, however, you can see that for the initial duration the user was looking into the camera, but after some time, my friend started to look into the camera and the algorithm could not identify her. Hence, the confidence score of the algorithm drastically dropped down to about 65 to 70%, and it kept the device locked. So now let's take a demo. So this is the first algorithm in which we are going to crop the image and we're going to collect the samples. So let's do that. And you can see that collecting samples is now complete. So for the next part of the image where we are going to train the model, and we're going to generate the training data and the training labels, and we're going to train our classifier over it. So here is where we will be doing the testing as well. So let's do that. And you can see that the accuracy is slightly varying, but it is able to identify me properly, and it's able to get pretty decent accuracy. So I can see around 89%. And let's see what it does when it's given an unknown user. So it will get stable. It's my phone that's causing the problem. So yeah, there you have it. Yeah, I'm moving my hand, so it's wobbling a bit, but there you can see that the initial accuracy is really high, as you can see above, and it's able to detect my face, and it's able to recognize my face. However, here you can see that the accuracy dropped drastically, and it's in the 70s range when faced with an unknown person. And because of my phone, it did vary a bit, but with a normal person, it will be able to detect the face, it just won't be able to recognize it. And the highest accuracy received we got during this trial run is 89.16. As we said, that's the average highest accuracy depending on the lighting condition and the quality of the camera that is being used. So let's get back to the presentation. So to summarize what we have learned is that the LBPH classifier is a very efficient and it's a very accurate face recognizing classifier. It's able to provide access control to the user during different environmental conditions of lighting, and it does so because of the Haar Cascades facial profile that we use. And although the profile is just for mostly frontal faces, you can slightly tilt your head here and there for just a few degrees, and you can even shift your head quite backwards, and it will still be able to recognize you and grant you access. Now, the algorithm's accuracy can be improved greatly with the improvement of the quality of the web camera that's being used. So if I did have a very good quality camera and better lighting conditions than in my room, say, then it would be able to properly recognize me, and I mean with really high accuracy. So for recognition with greater confidence, as we've said, the web camera with room light and everything should be a bit higher. So that's about it for the summary and conclusions, and this my report is now final, and I hope you guys liked that. So thank you.